Hi, today's lesson is on functions, and it's the 1.7 algebra lesson from the Glencoe McGraw-Hill Algebra 1 curriculum. So to start off, our new definition, our new vocab, includes function. So a function is a relationship between an input and output. And in functions, there's exactly one output for every input. The input we're going to use and call it our domain, and our output will be our range. So in this case, we don't necessarily know the relationship, but we need to be able to identify functions. So if there's exactly one output for each input, we can look at a set of data, for example in this case, and look and make sure that each input has exactly one output. So in this case, we do have that true. There's no repeated in the range. So this would be considered a function. As compared with the second example, where we have these inputs, and you can see that both 0 and 3 have an output of 6, or a range of 6. So this would not be a function. Or you could write not a function. Okay, I hope that makes sense. So the key point here is there's exactly one output for each input. So two more vocab words are a graph that consists of points that are not connected is a discrete function. So you may have a graph of points like this. That would be considered discrete. They're not connected to one another. They're each their own point. Where sometimes we're talking about the relationship between two things, and it might make sense to connect them. For example, if it was weight over time and you knew you were eating a certain much each time. So if you had something like this, then it might make sense to connect them. And that would be a continuous function because it has a continuous connection between the different data points. So let's look at an example. In ice sculpting competition, each sculpture's height was measured to make sure that it was within regulated height range of 0 to 6 feet. The measurements were as follows. Team 1 had 4 feet, Team 2 4.5 feet, and so on. So in order to begin this, we need to make a table for this data. So I'm going to set it up, and it's going to consist of our domain and ranges. So I know we have 5 teams. And here we're going to have domain is what we're putting in. So that's each team. So team 1, team 2, team 3, team 4, team 5. And our range, or our output, is going to be 4 feet, 4.5, 3.2, 5.1, and 4.8 feet. So the first step is to make that table. Then what we can do is we can go ahead and write it as a set of ordered pairs. So if we were to graph this, we'd want them in ordered pairs. So we'd want team 1. So if we imagine our graph is going to look the team number down here and our height in feet here. That means our X is our team number and our Y is our height. So 1, 4, 2, 4.5, 3, 3.2, 4, 5.1, and then 5, 4.8. Now, I've only shown you the positive or quadrant 1, but if you had negative numbers, you may need to draw your graph to include all the different quadrants. So we can now label our axes since we know what the domain is going to be, and then the range as well. So our range is going to go from 4 to 5.1. You know what, that's easy enough. I'm just going to number up to 6. So 1, 2, 3, 4, 5, 6. Now I can plot the different points. So I have 1, 4, 2, 4.5, 3, 3.2, 4, 5.1, and 5, 4.8. So now I have my graph. And then let's think about this. Would this be considered discrete or continuous? Well, in this case, team numbers really doesn't have a direct correlation or relationship to height. So these are each discrete points. Because the team number doesn't necessarily impact or tell you what your height has to be. Okay. So I have a try it for you. I want you to do this in your math rules notebook as an example. So a bird feeder will hold up to 3 quarts of seed. The feeder weighs 2.3 pounds with empty and 13.4 pounds when full. I want you to start off by making a table, determining the domain and range of the function. So figure out which is going to be the input and output, and that will help you figure out what is the x and y. Write the data as a set of ordered pairs, and then state whether it's discrete or continuous, explaining your answer. You may want to go back to the previous example to help guide you through this. So another way is if you are given a graph, you can do a test called the vertical line test to determine if that graph is displaying a function. And the way it works is you simply take a line and move it vertically, so you can think of your pen or pencil, you move it vertically through. And if at any point you touch 2 parts of the line at once, it's not a function. If you only touch 1 part each way, then it is a function. That goes back to the idea that when you have an input, there can only be one output. So in this case, this would be a function, because as we ran this through, we never intersect going vertically more than 1 point on the line. The second one, though, when we go through, there's a top and bottom that we're hitting. So this would be considered not a function. And this last one, going through, would be a function, because you can see here that this one's filled in, meaning that the axis is included in this part of the line, but it's an open circle above, so it's not included. If that were filled in, then this would not be a function, but since it's not included, it is a function. So that's a nice test you can do when given a graph to determine if something's a function or not. So equations that are functions can be written in a form called functional notation. For example, if you were given the equation y equals 3x minus 8, we can simply write that in functional notation by substituting the y with f of x. So let's try it below. If we were given f of x equals negative 4x plus 7, then find the value. Well, we want to evaluate this for when x is 2. So in this case, f of 2 equals negative 4 times 2 plus 7. So negative 4 times 2 is negative 8 plus 7. So f of 2 equals negative 1. It gets a little trickier. Sometimes you'll see something like this, where f of 3 is in parentheses plus 1. This means that this is getting substituted for the x, and this is done at the end. For example, if we were to plug this in now, still using this example above, f of negative 3 plus 1 equals negative 4 times negative 3 plus 7 plus 1. So that 1 gets added on at the end. So now we can use our order of operations. Negative 4 times negative 3 is going to be 12, plus 7, and then plus 1. So that would give us f of negative 3 plus 1 equals 20. So I want you to try these examples out on your own at home and bring them into class tomorrow. So press pause now. And the last example is considered nonlinear functions. So when a graph is not a straight line, it's a nonlinear. For example, the one you saw before, if it's curved at all, that would be a nonlinear function. And the way we get nonlinear functions is when we have variables that are squared or cubed or have those exponents. So here's an example of one we're going to try. And let's try it for when h is 4. We'll evaluate it. So in this case, it's the same way. You substitute it in. Negative 16 times 4 squared plus 68 times 4 plus 2. So I'm going to get my calculator here. So I have 4 squared, which is negative 16 times 16. So, but it's a negative, so negative 256 plus 68 times 4, 272 plus 2. And now I can get h of 4 equals negative 256 plus 272 plus 2 is 18. Okay? So that's all for today. And then tomorrow I'll give you a practice related to this.